Welcome, JEE Warriors, to what is honestly going to be the absolute best explainer on the internet for mastering electrochemistry. Seriously, today we're cutting through the noise and decoding the exact theory, plus those hidden advanced tricks you need to solve high-level questions. So let's just dive right in and start unlocking those top marks, shall we?
Here's our exact agenda for today. We're covering the JEE electrochemistry blueprint, cells, galvanic versus electrolytic, decoding electrode potentials, the Nernest equation, the delta G trick, and finally, electrolysis and Faraday laws.
Section 1, the JEE Electrochemistry Blueprint.
Okay, let's talk strategy for a second. Compared to massive, sprawling chapters like thermodynamics, electrochemistry requires way less brute force effort, but gives you a massive return. We are talking about a guaranteed 8 to 12 marks on the table. To put that into perspective, in the JEE, 8 to 12 marks will literally shift your rank by thousands of positions. So you aren't just learning chemistry today, you're actively claiming your rank.
Section 2, cells, galvanic versus electrolytic. Now let's quickly build our foundation by looking at the two main types of electrochemical cells. It's a complete contrast. A galvanic cell is basically a discharging battery. It uses a spontaneous chemical reaction to actually do useful electrical work. That gives us a positive EMF. On the flip side, an electrolytic cell is like a dead battery you have to plug into the wall. It converts electrical energy to force a non-spontaneous chemical reaction to happen, which gives it a negative EMF. And you've got to remember this core duality. The anode is always the compartment where oxidation happens, meaning it's where electrons are lost. Then you have the cathode, which is where reduction happens, meaning electrons are gained. So fundamentally, electrons are always going to flow from the anode, where they get released, straight over to the cathode, where they get scooped up.
Section 3. Decoding electrode potentials.
Let's test this with a classic scenario. Between zinc and copper, which atom do you think has a higher tendency to release electrons? Imagine dropping a zinc rod into a blue copper sulfate solution. Which one becomes the ultimate electron donor? Well, it's zinc. Zinc is way more eager to give up its electrons than copper. As it does, the copper ions grab those electrons and deposit themselves as solid metal, and that famous blue color of the solution just fades away.
This next part summarizes a massive chunk of theory into two really simple rules. A higher oxidation potential, that means the element absolutely loves losing electrons, making it a stellar reducing agent. A higher reduction potential means it loves stealing electrons, making it a super strong oxidizing agent. But hey, listen to this pro trick. Do not fall for the classic JEE trap of saying silver reduces. No, it's the silver ion, Ag+, that gets reduced, not the solid silver metal. Always keep an eye on your specific species.
Now, to keep all these potential values from turning into a chaotic mess, IUPAC mandates standard reduction potentials. So whenever you see that little not symbol next to the E, it means the potential was measured strictly under standard conditions. That means exactly 25 degrees Celsius, a 1 molar concentration for any solutions, and exactly 1 bar of partial pressure for gases. No exceptions.
Section 4, the Nernest Equation.
Okay, it's time for the heavyweights, the Nernst equation. This formula is literally your core numerical arsenal. It's the bridge that connects perfect textbook standard conditions to the messy, real-world chemical states. A huge chunk of your advanced numericals will just be you writing out the balanced cell reaction, calculating that reaction quotient Q, identifying the number of exchanged electrons N, and then using this exact equation to find your actual working cell potential.
Section 5, the delta G trick.
All right, welcome to the boss battle. Here is a golden rule. You can never, ever add intensive properties like E0 values directly together. It doesn't work. Instead, if you want to find a third electrode potential from two given ones, you have to follow 3 exact steps. Step 1, convert those standard potentials into standard Gibbs free energy, or delta G0, because energy is an extensive property. Step 2, add or subtract those new delta G0 equations. And step 3, convert that total delta G0 back into your brand new E0. Seriously, I cannot stress this enough. If you try to just add E0 values and skip that delta G conversion, you are practically guaranteeing yourself negative marking in JEE Advanced. It's a brutal trap. Mastering this specific trick is what separates the top percentiles from everyone else. It locks in your rank when you're hit with those tricky unknown potential calculations.
Section 6, Electrolysis and Faraday laws.
For our final frontier, we have to look at how we actually measure these chemical changes, and that brings us to Faraday's laws. It really boils down to this. In electrolysis, electric current causes a chemical change. The mass of the substance deposited is going to be directly proportional to the total electric charge passed through it. But here is the absolute golden rule. The equivalence of the substance deposited at the cathode will always equal the equivalence liberated at the anode. If you frame your equations in terms of equivalence, even the ugliest mass calculations become a total breeze.
So, armed with this mastery playbook, are you ready to conquer those advanced numericals and claim your 12 marks? You've got the foundational theory, the Nernst equation, the delta G trick, and Faraday's shortcuts. You're fully equipped. But before we wrap up, ask yourself this. The next time you look at a battery, are you just going to see a boring power source? Or are you going to see a perfectly balanced tug-of-war of electrons just waiting to be calculated? Use these frameworks, practice hard, and go dominate. I'll catch you in the next explainer.